My name is Harrison Leary, and this is my Physics 2 Lab 5. So the purpose of this lab was to display a real-life example of Faraday's law and computationally predict how a magnet will travel through a conductive tube. So as a result of this experiment, we recorded that there was an average fall time across 5 attempts of 1.59 seconds, while the model that I constructed predicted a fall time of 1.69 seconds. So a 0.1 second discrepancy. For the physics principles used, there's Faraday's law, which is shown as the integral of the electric field dl, which is equivalent to the negative change in magnetic flux with respect to time. And similarly, the magnitude of the change in magnetic flux with respect to time is shown here with this complicated formula. And then we have that the magnetic force is equal to IdL across the magnetic field, and that is also equivalent to the other formula shown here. And finally, the sine of theta is equal to mu sub m cross b sub m. So for the experiment itself, we took a conductive tubes, which it was conductive because it was surrounded with tinfoil, and dropped a magnet vertically, and the variable we measured was the time it took between entering the tube and exiting the tube. So what we measured for constants were the length of the tube, the width of the foil, the inner radius of the tube, the mass of the magnet, and again, the average fall time. Now for the model, the result of this model was 1.692 seconds, as the velocity versus time graph is shown on the right. And the discrepancy is most likely due to rotation of the magnet as it falls, as in the model it is depicted as completely perfectly along the z-axis, while in real life there is some rotation across all axes. And additionally, there is a slight error in stopping the timer when it exactly meets the end of the tube. Now for the code for this model, we put in the necessary constants, and then for visualization we had to define the dipole moment as well as the change in magnetic flux, which are shown in the bottom left portion. Then we dealt with the forces, so we had the force of gravity, the magnetic force on the magnet, again the change in magnetic flux, and then finally, using all of this, we did the magnetic field along with the F-net, and finally updating the velocity and position with respect to Newton's law. So finally, for our conclusion, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So if we reduce the resistivity of the conductor, we will be increasing the current, and with a higher current, this will mean a higher magnetic field strength, so the magnet will be falling faster. Now, additionally, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? So by reshaping the tube and having holes or slots, that's essentially, in a simplified manner, lessening the amount of rings that are in our tube in our calculations. Therefore, the magnitude will decrease, and the magnitude of the magnetic field will decrease, and the magnet will fall faster. That's it. Thank you.